Now, of course, we have here solved for V, but we might ultimately want to know what E is. And we, of course, have the relationship that E equals the negative gradient of V. And so we get as our answer V naught over LZ hat. And that reminds me, I believe I may have made a mistake here. I forgot to put that minus sign in. It doesn't actually matter for the conclusion that, Laplace's equation, because minus sign is once you do the Laplacian to v, it equals 0 anyway, so the plus minus sign doesn't matter. But for the sake of being accurate, just note that earlier in the lecture I misspoke. So based on this relationship, this is where we get our directionality, and that, by the way, is why I drew the E field going this way. Okay, now while the resistivity and conductivity are microscopic properties. Again, when we were talking about this in the first lecture, these are properties that refer to a local neighborhood. They're also, I would kind of call them local properties. Um, they are independent of geometry. And I've already said this, but I'm now going to take it further. Resistance, and that's resistance as opposed to resistivity. Resistance and its converse, which is conduction as opposed to conductivity, are macroscopic properties that do depend on the specific geometry. In other words, they vary from problem to problem, case to case. This relationship here, or rather this approximation, is generally true, regardless of geometry. But taking that sort of to the v equals IR level is geometry dependent. And I'll remind you from earlier in this lecture, where you have a complicated situation, the general case always applies to that small neighborhood. But if you want to know what's going on in the bulk material, you have to add up all of the little pieces, all of the little neighborhoods, all the little voxels. In other words, you're going to be performing an integral. Okay. So let's go back to our wire, and I'm just going to redraw it. It's okay. But we're going to bear in mind that this cross section has an area A. And again, remember, this is v equals 0. Here's the rest of the wire. This is v equals v naught. And this is E equals negative v naught over L in the z hat direction. And let's write out the microscopic Ohm's law. So the current density is equal to sigma naught E. This is, again, microscopic Ohm's law. And you will recall definitionally, if you want to go from current density, which is current per unit volume, to a current in the sense of I, that's going to be equal to the current density times the cross-sectional area A. Okay, so that's uh, current density, and this is cross sectional area A. That being the case, we can write I equals sigma E A, which we can write as sigma V naught over L times A. And we can then write that as I equals sigma A over L times V. And now we are coming dangerously close to the version of Ohm's law that you all know and love. Ohm's law is usually stated as V equals. So what we're going to do is we're going to multiply this over to the other side. And what we're going to get is V equals L over sigma A times I. In other words, V equals IR, where this is R. So in the particular formulation of, or in the particular context, I should say, the particular geometry of a wire, R is equal to L over sigma A, or another way you could say it is R is equal, because resistivity is 1 over conductivity. R, the resistance, is equal to the resistivity, rho, times L over A. And this is a common relationship that many people know, but we were able to derive it by essentially calculating the E field and then sort of integrating out over the geometry. We got that cross section A by integrating over the geometry. And so this is the case for a wire. And what does this tell you about a wire? It tells you that if you increase the area of the wire, the resistance is going to go down. So bigger cross sections of wires have lower resistances, and it's an inverse proportionality. If I double the cross sectional area of the wire, I will have the resistance of the wire. And it tells you that length is directly proportional to resistance. So if I have a wire of a material with a given resistivity, if I double the length of the wire, the resistance of that wire goes up by a factor of 2. And so that is the relationship for resistance in the case specifically of an axial arbitrary wire. Okay. But unfortunately, again, that is one very specific geometry. What was specific about the geometry? What was specific is that we were applying the voltage purely to the equal potential is on the surface of each side of the wire. And there is an axial geometry. And so this problem is constructed in a way that there is no radial component because the charges cannot leave the surface. And so we have a very specific symmetry to this problem. And I want to point out to you all that that's an important part of doing E&M, or understanding E&M, or being effective in this subject, is being able to see or understand how a problem simplifies for a particular geometry. And we're going to now look at a different case in order to see how this relationship can change in a more complicated problem. I'll also point out that while I was saying integrated over, it might not be obvious to you that we integrated over when we got this relationship here, but that is because, in a sense, our integral was sort of summing over A, and it was based on our knowledge of the fact that everything we were integrating over was constant over the surface and over the bulk in the radial direction. And so it was really, when you integrate over an area where things are constant. So if I was, integrating over a thing, let me actually write it out this way. If I was integrating over some function, r whatever, over an area, if I was doing an area integral, if it's constant over this, I can take the function out if it's constant, and then I just get the area out. So all I'm saying, and that was a little bit hand wavy, which is why I'm not going to keep it in my notes. All I'm saying is that technically the integral was implicit when we wrote out sort of that formula there. But now we're going to do a problem where we're going to actually have to do the integral.